Hi, folks. It's Monday afternoon. Going to do hopefully a quick video on things we did last week with 10.2 specifically. So 10.2, specifically classifying the equilibrium point 0, for phase autonomous systems using both a trace determinant plane as well as eigenvalues. Keep in mind our last video, we took a plane autonomous system, found all its critical points. We ended up finding 4 of them. We found 0, 0, 0, 18, 14, 0, 10, 8. For right now, in our class, we're only classifying 0, 0. When you come back from break, we'll classify these others. So 0, 0, when we go to classify it, we're classifying based on eigenvalues and then this trace determinant plane. So let's do that. Let's look here. Let's switch to, I don't know, gray. Okay, so let's say this is our phase autonomous system, and we either found or were given eigenvalues 1 and 5 and associating eigenvectors. Well, the general solution, well, let's say 2 things. I guess one, the eigenvalues are distinct real of the same sign. They're both positive. Both lambdas are positive. So same sign means 0, 0 is a node, and that both eigenvalues are positive means we have trajectories away from the equilibrium point 0, 0. There's growth away from. The particles move away from in our phase determinant or phase portrait. So this is unstable node. If they were both negative, -1, -5, then it would be a stable node. Then, so that's telling us how to use eigenvalues to determine stability and determine what type of equilibrium point we have, in this case, a node. The other way is to use the trace determinant plane. And let's first find the determinant. That's negative 7 plus 12. Negative 7 plus 12, that's 5. If we look at the trace, that's -1 plus 7. -1 plus 7, that's 6. Let's see, the determinant being positive puts us in quadrants 1 or quadrants 2 of your trace determinant plane. Here's the determinant is the vertical axis, and we're positive. So we're above the trace axis. We're in quadrant 1 or quadrant 2. Then the trace is also positive. Trace is also positive. That restricts us to quadrant 1. Here's the trace axis. We're positive. So we're in quadrant 1 there. And we have to be either a node or we have to be a spiral point. And that depends. So depends on where we are in our region, in our quadrant 1. We're either above the parabola up here or we're below down there. And you can do that by comparing trace squared minus 4 delta equaling 0. So if we solved that and we said, let's see, let's move the 4 delta to the other side. Trace squared is equal to 4 delta. If trace squared equals 4 delta is when you're on the parabola. If 4 delta is bigger than trace squared, then you're above. And if 4 delta is less than the trace squared, then you're below. So look at those things. So 4 delta, how does it compare to trace squared? 4 delta is going to be 20. How does it compare? Let's do this. 4 delta is 20. Trace squared is 36. Let's see, that piece was right there. Okay. So that's less than. So we are below the parabola. We're down here, and our equilibrium point is an unstable node. We're below all right, we're below the parabola and trace determinant plane. So 0, 0 is an unstable node. A general solution, you know what I'm going to need to put in? Actually, I'll move this lower. And let's do this. Let's move. Let's put that over there. Put that there. And then this here. Okay, so last bit on that problem would be to plot. So with, let's see, we don't need a general solution. We could just plot given our eigen vectors 1, 1, and 1, 3, and knowing the signs of our eigenvalues. So if we plot 1, 1, 1, 3, let's do this. This is a phase portrait, is what we're plotting. Phase portrait. We know it's an unstable node. So let's take the eigenvalue of V1. That's 1 in the X, 1 in the Y. So if we went over 1, up 1, there's V1. I need a gray. Let's do a gray. There we go. The eigenline that associates with 1, 1 is this line. And we know that its eigenvalue is a positive 1. That means the flow is away. Put some trajectory arrows like this, showing the flow is away. Then we plot V2, which is 1, 3. V2 is over 1, up 3. 1, 3. There's V2. Here's its eigenline. Flow is also away. All right, then let's see. Our general, I do maybe want to write our general solution, and the general solution is x of t would be c1 e to the lambda 1 t v1 plus c2 e to the 5t 1, 3. And then let's see which term, how would you draw your solutions? This term goes to infinity faster, and let's see, this one goes to infinity slower. Which term dominates the solution? Which term? Which term pulls particles away from equilibrium at a greater strength? I believe it's this one. So as terms move away, or as particles move away from the origin, I believe. So let's say this line is our eigenline for V2. It came from eigenvector V2, which was 1, 3, and it corresponds to the stronger term in your solution. So this term, stronger term, it between the two. Here's one term, here's the other term, and this is the stronger one, and it pulls particles in its direction. So if you had a particle, say here, it would curl this way if you had curl towards that line. Maybe it starts out going this way, but then the current of this other stronger line. So the orange particle might start out going this way, but the current of this other stronger line pulls it that way. Then this and this, if we had another particle, let's use green over here, say here, might start out going that way, but then it's going to curve and follow the trajectory of the stronger eigenline. All right, let's work through one more, and hopefully maybe a touch quicker, just to save y'all some time. All right, here we have another phase autonomous system. Here are its eigenvalues and eigenvectors. Notice the eigenvalues are distinct real this time again. So distinct real eigenvalues of opposite signs will classify 0, 0 as a saddle. All saddles have flow in towards the equilibrium and flow away. The lambda 1 being 2 bigger than 0 matches flow away, unstable flow away. Lambda 2 being negative 1 less than 0 describes stable flow in towards 0, 0. If we used the determinant and the trace to handle that, let me go. Determinant and the trace. Let's switch colors to green. So determinant is 3 minus 2, that's negative 6, minus a negative 4, so plus 4, that's negative 2. Less than 0, we're in quadrant 3 or quadrant 4, and anytime we're in region quadrant 3 or quadrant 4, we're an unstable saddle. It's an unstable saddle for everything below the trace axis. If you, well, then there you go. You don't need to find the trace for that classification. So we automatically know. So 0, 0 is a saddle. You could write it as unstable saddle or just saddle. It's all unstable in the saddle case. Then if we go to plot, let's write our general solution. XT general solution is what? C1 e to the 2 t11 plus c2 e to the negative t 14. If we go to plot those, 1, 1, and 1, 4 are eigen vectors. There we go. So 1, 1. I need to do a better job. There we go. So 1, 1 is here. One, it's associating eigenline. There's the line there, y equals x, and it associates with a positive eigenvalue, which is 2. Positive meaning the flow is away and unstable. Then the vector 1, 4. 1, 2, 3, 4. There we go. The vector 1, 4. Here, that's v2. Its eigenline is this line in gray. It has a negative eigenvalue, associates with flow in and instability. And we, in our general solution, don't need to worry, I guess, about a dominant term, although this is the stronger term. Stronger term because this one decays to 0. Either way, if you had a particle, say here, it would flow in to match this flow over here, but then as it gets closer to equilibrium in this region, it's going to flow that way to match that eigenline. So something like this. Another particle, say in green, might do something like this. Say the particle's there, it's going to flow that direction. It's going to flow according to the blue and then curve and flow according to the red. If you mapped a trajectory in these other regions, the trajectory would look something like this. And then here. There we go. Notice the trajectory arrows on your paths match the flow that's in your picture. There we go. There we go. All right. There's your saddle point. That's a quick, well, it ended up being too quick, but you could watch fast your classification of the equilibrium point 0, 0 for phase autonomous systems, and using both the trace determinant plane that you see here, as well as eigenvalues. Y'all take care. Have a good holiday. Be good to yourselves, and I'll see you in a week.